Hello, I'm Anna Mackay and this video is on motion or kinematics in the topic of applied calculus. So for my students, everything that you see typed on your screen, you'll be given as a handout, so you won't need to write down anything that you see typed. So I'm going to quickly go through some of these points here, but you can always come back and pause and read them longer. So displacement. Suppose we have an object, P, that moves along a straight line so that its position S from an origin O is given as some function of time t, and that function is S of t. And S of t is a displacement function, and for any value of t it gives the displacement from O. So where that particle is in relation to the origin. So we're looking at the motion of a particle. Velocity and acceleration are, velocity is the first derivative of that displacement function, and acceleration is the second derivative of the displacement function. When you see initial conditions, that's referring to when time is naught, and so we're after S of naught, V of naught, and A of naught. Here is some useful tables. I'm just going to skim over them to do with the signs of S, V, and A. I'll leave you to read back over that. We've got to move on, so this video isn't too long. This table is also quite useful, looking at when t is naught or when S is naught. That means the particle's at the origin, and if V is naught, then the particle is stationary. I'll leave you to absorb that, but the really important one is down here. We'll come back to this, that if the signs of V and A are the same, so either both positive or both negative, that means the speed is increasing. Whereas if the signs of velocity and acceleration are opposite, then the speed will be decreasing. If you've got a background in physics, this won't be new, but for those of us that don't, let's push on and see if we can understand this a bit more. If you get a question asking you to work out a motion diagram and distance travelled, here are some useful steps to follow if it's not giving you any other steps. I'll leave you to digest them in your own time. Let's get on to the example. We're only doing one, but it's got lots of steps to it. So the position of a particle travelling in a straight line is given by this function of S, where time t is in seconds for time greater than or equal to 0. First of all, we want to find the position of the particle for this time. So where is it? So we simply substitute this value into our S function. So let's do that. We've got S of ln4, and where we see a t, we're going to put in an ln4. So 3 to the power of ln4, take 4e ln4. We use this as a practice using our log laws, well, simplifying that. So e to the power of ln4 cubed now. And this rule that the answer here will be 4, times by 4, and the same rule applies here. The answer will be 4 cubed times by 4 cubed. That's 16. Now if it doesn't ask for an exact value, feel free to use a decimal equivalent. So we've got approximately 5.33, and that's in meters. So that's where the particle is after ln4 seconds. Moving on. We need to find expressions for the particle's velocity and acceleration and then draw sign diagrams for them. And this time it is asking for exact form. We need to leave our calculations in lnk. Here's our function as a refresher. So we need to differentiate. So first of all, let's do v of t. Now that's the equivalent of s dashed of t. So the first derivative. Copy and paste the e function and then differentiate the power. So we have e to the power of 3t and differentiate that power. And the second term as well. We'll tidy that up. The 3's will cancel out and we're left with e to the power of 3t, take 4 e to the power of t. Let's solve that for when that's equal to 0. So that would be when our velocity is 0. Might just do that in another colour. We're working out e to the power of 3t take 4 e to the t when that's equal to 0. So we have to factorise that, taking out a common factor of e to the power of t. Now, solving for when each of those are equal to 0, you may remember that the e function is always greater than 0, so we can just knock that one out if you like by writing that. Solving the second one, now to get t down out of the power you would need to log both sides, so putting in a natural log, and if you're comfortable with that, that goes straight to this line here. Solving for t, divide by 2 or times by 1/2, and that's also the same as ln 4 to the power of 1/2, and then t, oh I've run out of room at the bottom here, that's equal to ln 2. And the decimal equivalent for that, because we're going to need it later, is, well actually perhaps I'll come back and tell you when we need it. So the second part we need to do is find the acceleration function, and that's the derivative of the velocity function. So we have a of t is equal to v dashed of t, and that's equal to differentiating this function here. So we copy and paste the e functions and differentiate the power. I'm just going to be cheeky and squish the 3 in there. Now we need to solve for when that's equal to 0. So perhaps I will use another colour. Factorising out a factor of e to the power of t equal to 0. As we've said before, e of t is always greater than 0. So solving the second one, we've got 4 on 3. Natural log on both sides leaves us with ln 4 on 3, and then divide by 2 or times by 1/2, and that's putting that fraction to the power of 1/2, which is the same as doing a square root, and so we've got ln of 2 on root 3. Now we need to draw a sign diagram for this, so we need to know when they're positive and negative. So this is now going to be when it's really helpful to create a picture, a graph of this. I'll refresh your memories as to these two a little bit later on. Let's go, so there's one value for each, one for the velocity and one for the acceleration, so where a change might happen. So let's go to our calculators now. Here's mine over here. Now here's our function already typed in. You type yours in too. And graphing. Now technically we don't need any time less than 0, but if you're in a standard view window, let's just, well no actually let's get rid of it. So we've got 0 for our x, and here's our function. Let's just zoom in a little bit. Let's just take our x to a max of 3 so that we can see a bit more closely what's going on. Okay, so as we said, we've got one time when the velocity is equal to 0, so that's a stationary point. Looks like it's somewhere down here. And so what's the slope either side of that? So coming into that slope, it's a downhill line, so that's negative. So we're going to have negative, then positive. And for acceleration, there's a change, as we know, happening somewhere around ln 2 on root 3. And so past that, it's really easy to see. That's concave up, so that's positive. And prior to that, it's negative. So both of them go negative, positive. So let's go back and, okay, so drawing ourselves a sign diagram, we've lost these values, but how I like to draw that is I like to put them both on the one sign diagram. And I'll show you why. So we've got our time is always greater than 0. Use a ruler to be nice and neat. So this is our v function, and this is our a, v of t and a of t. Now those values that we're after for v, it was, I'll perhaps right off to the side, ln 2 and ln 2 on root 3. The decimal equivalents, just put them in your calculator and work them out, 0.69 and 0.143. So thinking about which one's further along, ln 2 is, doesn't really matter where you put them. And the other one is the ln 2 on root 3. Now, the signs, we said they both go negative, positive. So we've got negative, positive, and negative, positive. Now, have we answered the question? Find expressions for the velocity and acceleration and draw sign diagrams. Yes, we've done that part. The next part is we're going to go back to our sine diagrams. We need to find when the time interval for when the speed is decreasing. So that meant if we go way back to a table that we had here, or some words, when is the speed decreasing? When the signs are opposite. So let's go back to our sine diagram. Here we are. This is what I like to do. You take that point here and just do a little dashed line up to the other sine diagram, and same on there. Sort of connect those 2 points and then fill in the signs either side. So because that is not a real critical value that we're interested in, it's still negative in this whole region, and same for here, this will be positive in this whole region. Now it's really easy to see when the signs are the same and different. So acceleration and velocity are the same after ln2, and acceleration and velocity are the same prior to ln 2 on root 3, and they are different between those two values. So it's really easy to see when you do that to your sine diagram. That's just one option. Some people will see it really quickly and easily. And so we just have to write that as an interval, ln 2 on root 3, and t is less than ln 2. So that's that part. The last part, no, second to last part, find the initial conditions and hence describe the motion at this instant. So initial conditions are when t is 0. So we're after when t is 0. So we're after s of 0, v of 0 and a of 0. So feel free to use your calculator and the trace mode for this. Just to save us some time, I'm just going to answer these for you. So you can also substitute in t of 0 into each of these actual functions and work that out. The velocity will give us -3, and the units is meters per second, or meters s to the -1, and the acceleration is -1 meters per second squared, -2. So, and we need to describe that. So this is a sentence that we write, and write this type of sentence each time that you get asked to describe the motion. The particle is, so you go down the list and you answer one at a time. So this describes where it is. It's 3.67 meters. Now look at that negative sign. That means it's to the left. If it was positive, it'd be to the right of the origin. So you've used that piece of information. Describe the velocity now. So you say it's moving. Which direction? Because it's negative, that means to the left. If it was positive, it would be to the right at 3 meters per second. And now describe the acceleration, and has acceleration, and we just state that value, -1 meters per second squared. Okay, last part, drawing a motion diagram for particles and finding the total distance travelled in the first ln4 seconds. Okay, so a motion diagram, what we need for those is where the particle starts, where it changes, and where it ends, if that's relevant. So we can get that off our graph as well. So in your graphics calculator using trace, you're interested in s of 0, because that's where it starts, and that gives us, as we've already worked out before, this value. Where the velocity is equal to 0, so that's where it changes direction, and that's that value there, -5.33, and then when sometimes it asks you, it stops at a certain point, and this time it's ln4, so s of ln4 is +5.33. So there are values of interest. To draw a motion diagram, we draw essentially a number line, and this is representing S, and these are the values that you're going to put on there, as well as the origin. It doesn't have to be exact, so we've got our largest negative value, our next negative value, always put 0, and the final value. Now, where does it start? So when t is 0, it starts here. So we will put a point there. Some people like to write t is 0. Then where does it go? Time passes and it goes to negative 5.33. So we often put an arrow to show the direction that it went. And now it changes direction and ends up at positive 5.33. So instead of drawing a line across the top of that line, because it might get confused, we tend to draw above it like this and put an endpoint. You put an arrow for the direction, and if you like, you can write the time. You don't have to though. So that is a motion diagram, and we need the total distance. So thinking about where you start. So first of all, we need to calculate the distance between here and here, and that's the difference of these numbers. So I'll just use some of the positive versions of that. And then we also add on the distance from here to here. So we've got this distance from negative 5.33 to the origin. So that as a distance is positive 5.33, and then another 5.33 to get to the final point. And the answer is 12.3 meters. And that's the end of our motion question. If you like this video, give it a thumbs up and subscribe to the channel. And the next video in this series will be called Rates of Change. Thank you.